So when we open up to page 367, as you can see, there's basically a flow chart there. I don't know, maybe you would say, man, I like that one a lot better than what's in front of us. In other words, what we're looking at here is something like this. I don't know, maybe you won't be able to see that very well when you look on camera. There's also one on page 366, okay? In other words, what we're looking at here is, as you can see, addition reactions, and that is on page 366. And just out of your first, let's say, observation, why does it look like on page 366 those are all addition reactions? And on page 367, when it talks about aromatics, what type of reactions does it say we have there? Okay, so aren't these both alkenes, though? Which they are. Yes, they're both alkenes. It's just what would be some of the fundamental differences between the aromatics and that of the alkenes on 366. Other than the structure. We know aromatics, okay? Six-sided figure. And then what does the circle tell you? Okay, yes, that is benzene, but it's telling you something about inside the ring, though. Okay, and there's alternating double bonds, which is what alkenes really are. So one of the things I want you to look at on page 366, when you look at the bottom there, it says you have X2, okay, that's the second one down. So remember, X is just any halogen, the same on this chart as it is on, you could say, yours. You have H and X, which means what? You have hydrogen and any halogen, and then you have hydration, which just means you're adding water, and that's the only thing you're doing. But what do you notice underneath the arrow on those three reactions? But then what's the exception with hydrogen on the very top? Okay, yes, you have to have a catalyst when alkenes are reacting with that of hydrogen, okay? So the bottom three, there is no catalyst there, okay? So why is it that those bottom three do not have to have, well, we're not worried about the hydrogen because it's, when we look at those bottom three, do you remember why do we have to have a catalyst for those, or excuse me, why do we not have to have a catalyst for those? But when you look at the aromatics, there's something written above and below the arrow each and every time. Why might that be? What's the stability of aromatics? Are they unstable or highly stable? The aromatics now. They are extremely stable, okay? Because they have those alternating double bonds in there. So whatever it is that you are adding that to that ring, you have to have a catalyst. That's not the case with the alkenes or aliphatic compounds, with one exception, and that, of course, is hydrogen. Okay, so when we look at substitutions, when you look at that ring on the right side, whether it's halogenation, nitration, sulfonation, and alkylation, okay, what do those red letters represent on the ring? I should say, what used to be on the outside of that ring? And we've said it before, I just don't know if we remember. Okay, so let's look at one of those reactions. I don't care which. Probably not the sulfonation. So the nitration, okay? So one of the things we know, we've got this benzene ring, and we want to do a process of nitration on there, okay? So we know that we're probably going to add some nitric acid, and it's just more commonly wrote like that. Again, you probably have never seen that before until now, because I think if I would look at that the first time, that doesn't make any sense. But once you go through the process of the reaction then, and I think, what does it say? Have H2SO4. Yeah, so we just put SA here for that. So that has to be present, okay? So we can presume what's going to happen now. What happens to what we see here? Okay, it splits in half right there. And then is this something going to attach? Are we going to make a phenol out of this or nitrobenzene? Right, because this then attaches onto here. But what is unseen on the outside? We just don't put it on there because this circle accommodates for two things. One, the double bonds on the inside, and the hydrogens on the outside. So what that means then is there used to be a hydrogen here, but now we're going to put that nitro group on there. Okay? So that hydrogen just doesn't disappear, because don't we have something left over here? I don't know if it says it on, no, and it doesn't say that on your chart there, and it doesn't say it on yours either, I don't think. But since there was a hydrogen here, what's left over in this compound here? Right, so it's going to give us some water at the end. So as you can see, even with this chart, we're not too concerned what our products are, whether these are balanced. We're just mainly concerned about what it is that we're making. Okay? So it's the same out of this author as you could say what you have in front of you. So, and then some more of this content we could say is, now if you look at page 362, okay, now you see just a lot of this, they just color code a lot of that for you. And I think we've talked about each and every one of these. We've done the alkylation, we didn't do sulfonation, we just did the nitration, and I think that we've done halogenation then as well. Okay, so I just wanted to introduce that to you, that of course we're just not making this, taking this content out of, we're just making this up. And I think you'd probably know better than that, because we really want you to be prepared for this for the next time that you see that. See this? Yeah, that you would see this. All right, last thing I want to do, then we'll open up the floor here. And that is, when you see the example on page 364, some of you had asked that yesterday. What do you notice about that example in page 364? That you have an aromatic benzene on the bottom, and if bromine is added to that. Now, notice that moving forward, this is how I prefer to write, because I think this is what makes the most sense to you, and I think you would agree. But that bottom reaction is showing you this. Okay, so notice that they have the arrow here. What do you suppose that means when bromine is on top? That's what you're adding, okay? So, and I don't know what it'll be like in your future, whether it's written like this, and then you have to have a catalyst of some sort. So I don't know, maybe it's, is it FERBR3 or something like that? Below the arrow, yes. So this is what you might see in the future. It just means what's on top is what you're adding. This is your catalyst. But we take a very similar approach. So to me, I think we learn better this way. Okay, so we're going through a process. You could say bromination or halogenation means the same thing. But the top ring then, okay, what do we see that's different between the bottom one, which we just did, and the top one on page 364? Yeah, it's not a benzene, so it shows that there's a double bond there, and they're also adding some bromine. So would we have to have something here? You are correct. Why not? Because what's the major difference between these? Because your classmates said it. This is not what? That's not benzene. So this is really, really unstable. So you would not have to have a catalyst for this. This will proceed and move forward. So we just like to make you make correlations here and observations that in that problem, I think that's not quite where the double bond was. I think it was down here, it was up there, and I think it was chlorine instead of bromine, right? So for our purposes, what we're saying is, and again, it's just making these observations that what's going to happen between here and here? What's going to happen to those double bonds? Yeah, they're going to break, disappear, whichever. So wherever it is that you see a double bond, what do you attach to the ring? Yeah, your bromine. And then, like in yesterday's example, it was the chlorine. So wherever that is, we would put bromines down here. And one of the things you might say, well, according to yesterday, we said that that would attach to both sides where you only have two. It's a diatomic molecule. Yes, we understand that. You would do both because there's two double bonds there. That is how the perception that we want to take moving forward. And then what we see happening here is, notice that this was never balanced to begin with. Who's to say that now you could probably go, and then you're going to say, well, we got 4 of those. But our main concept or goal here is to notice the difference. If there's just one double bond on there, that breaks, and then your halogen's attached to wherever those double bonds were. All right. So any other questions that you want to look at on your paper? I'm going to hit pause for just a moment. Question number 9 is asked. Said, I'm going to be mean today because I just feel like I got this mean streak in me. Grrr. Okay? So you can make some presumptions or correlations here with number 9 and this problem. And then notice we have that. Okay? One of the things you're going to notice that when we get to the alcohols and moving forward, this and have something in common. And then this is another one. Trying to remember. Okay. This is not a very strong oxidizing agent. I can't quite remember off the top of my head if there's a 2 there. But these 2 are written correctly. These 2 are extremely powerful oxidizing agents. It's not because of the metal ion that we have here, the positive one. It's these guys right here. Here, here. And again, we said this one's really, so I'll put a triangle around. So we kind of keep that separate. This one isn't quite as powerful. And again, don't make the correlation just because there's a 7 here and a 4 there. No, that has nothing to do with it. This is called potassium permanganate, and this is potassium dichromate. You could also have sodium dichromate, because remember, it's not the metal ions that make it such a powerful oxidizing agent. It's what we see inside of here. So on your flow chart, that you have, I always like to say this is one that really doesn't play by the rules, really, because it's kind of sitting off in the corner. It's kind of all by himself. Okay? So even on your flow chart, upper left-hand corner, what do you notice is the difference? And I should really redo this flow chart because, yes, it is helpful, but what it should have on there is probably something like R and R prime or something like that. That just means these alkyl groups, there could be 1, there could be 2, there could be 3, but notice you have R, 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 R. Those R's are a variable for what? Yeah, not just CH3, it can be. It can also be CH2, okay? It just means an alkyl group. So this is an alkyl group. Just like you correctly pointed out, that's an alkyl group. That's, CH2, CH3. I'm going too fast. The hamster's sleeping upstairs. He's kind of taking a break. That's an alkyl group, and of course we see that this is an alkyl group. Okay? That's methyl, that's ethyl, and then of course what type of group do we see here? And it wouldn't matter if this was a butyl, a pentyl, an isobutyl, any one of those. According to your chart, what happens to each and every one of these bonds from here on out? According to your chart, does it have, we know that this is going to react, okay? And I think you have to have a catalyst too. Does it say that? Heat, okay. So then we know that this is going to react, but we don't add all of these groups on here. What does it show on your chart? Exactly. So the main thing we could say, and that would be correct, that's half of our benzoic acid. What are we missing? Yep, the OH. It does not matter how many of these alkyl groups you have on here. Well, I mean alkyl carbons. Like I said, you could have 7 of them out here. Each and every one of them is going to break. You get benzoic acid. Okay, there's probably a quicker way to explain that. I should have looked at the clock down here and probably said 15 and a half minutes. Now we're up to 18. I don't know if that's right. Okay, next question to help you out.
Wait, so what if there's a methyl group off it?
If this is just CH3,
Yeah.
it's still going to make benzoic acid.
So either way, if it's K and then
Yep, any one of those that we had here, maybe not that bottom one, but we're going to spend the most time with these top 2 because they're such powerful oxidizing agents.
where's the K and then go?
Oh, let's see here. That is a good question. I don't know. And we could look here, and it doesn't show with the author either. And that's a question that, oh, okay, yes it does. You got CO2 and H2O. So I suppose it's safe to presume that these carbons, okay, grab onto some of that oxygen, okay, making your CO2 and then plus H2O as well. So again, we're not concerned about that. We just want to know that this is going to make benzoic acid. Did you say 13? Okay. I just need to have a quick look at.
I don't have paper.
Oh man. That's probably pretty hard to do then. Oh my gosh, I feel terrible. But before I give that to you, I'm going to look at number 13. Okay. Okay, the next question was number 13. So I'm going to be lazy today. It feels like one of those days. I don't have to erase everything, just most of it. Okay. So number 13 says you have benzene, and we're going to react that with some ethene. Okay? Would you believe, I'm going to make you think a little bit, that is on your chart. Okay? And we'll give you a little hint. And for those of us tuning in, we're number 1. So where are we looking at the clock? That's probably enough. 1 o'clock. Okay? What happens at what? Well, I mean, is everything? Do we like looking at 1 o'clock during the day, or you're not in here, so it can't be as great as what it is right now. Okay. So what that is saying then, if we have an alkene, okay, and then I would presume that there's probably there has to be a catalyst here of some sort, and it's another acid, so H2SO4 or sulfuric. Okay. So at 1 o'clock, according to your chart, you have benzene, you have an alkene, you have a sulfuric acid catalyst. What does it tell you over here? What gets attached? Yeah, and remember, what is R? That's X, yep. Yeah, alkyl group. So in this case, we've got 2 of these, so they're not going to disappear. And then what else would we have? Close. Okay, now, and this is the response that I would expect. It doesn't mean that you can't handle this. It doesn't mean that you won't handle this. This is why sometimes maybe the structural formula is better than the molecular type. So if this is what happens, that R, this is R, if it gets attached, let's look at our structural formula. So same thing, two carbons, okay? And then we have all these hydrogens out here. There's 1, there's 2, okay? So how many bonds are available for this carbon? You can put 3 more of them on there. Okay, so 1, 2, 3. You might be looking at this and say, we're either doing some magic here, or why is this happening? But you also have to remember what type of reaction happens with these aromatics. Something we said a long time ago. It's not addition, it's substitution. So just like yesterday, a substitution was Mrs. Paulson was in, substituting for myself. Everyone's saying, oh, it went so great yesterday, he's gone. I don't know, maybe not. So you got to remember there was a hydrogen on here to begin with, so that then attaches to that carbon. So that's how you get C2H5. Okay? So it does get tricky. Don't think that you have to write it like this. Okay? If you take this in college, worry about it at that time. Because if we can understand this transition then is going to be hopefully fairly simple for you. And the reason I know that is because students have done that in the past and have been quite successful. Okay? Anything else? Because we've done a lot of difficult concepts. Okay, we were just discussing that there's some concerns. I don't want us up all night trying to figure this out because we were just saying that nobody wins, and that's except me. And like I said, I'm making them stay. No, I don't want you up that late. Okay, so 16, okay, I believe it says this, right? Okay, so what we can presume from this is we probably have to have, I'm just going to put nickel chloride down here. So we know this is going to react. Okay. So what I want you to look at here, first of all, are you starting in the center of your flow chart? Yes. You are correct, but why are you right? Because we don't have anything on here. It's just benzene here. So what you need to look at on there are variables for this. Because what is a propyl group? Is there a variable for that? So notice we don't have that would be propane. But how could we change that to propyl chloride? Okay, that's in a manner of speaking, yes, but we wouldn't take it off. I know I'm being mean when I say that. We don't take the hydrogen off, we just replace it with that chlorine. So this would be our propyl chloride. So where on that chart would you're not going to see propyl chloride on your chart, but you're going to see the variables for it. Right, because remember earlier, that's an R group. That's an R group. That's an R. And like I said, we could keep on going. Those are all R groups. Okay, we can't just add this to a ring. Because if that was the case, we could say, well, if we just had this R, or this R, okay, well then that's given us our toluene. But that is not correct. It can't do that. You just can't take an R or a methyl group and say, look, here's the letter R. We got our toluene now. That's not how the reaction proceeds. But it does if you have R and X, R and X, R here, and X. So the alkyl group right here, this is our R, and then here is our X, or a halogen. So then, according to this, we don't make toluene, or excuse me, I better erase that. Does it say that R is going to attach to the ring, according to your chart? Yes, but keep in mind, I like it when there's coincidences like this. We got this box here. Notice it doesn't say that, does it? No, the X is too much. So what we can presume is that if R attached here, which it does, okay, and what was on here to begin with? A hydrogen. But, okay, so we're not quite putting it together yet. There was a hydrogen here, so we wouldn't write HX, because what is X? Excuse me. Right. plus Cl. So now, since R has attached here, okay, we're not going to write just letter R, but what's inside that box. There's two answers you could give, the molecular formula or the structural formula. C3H7. Darn it. C3H7. Or if you are a molecular formula person, you can also do that. We're not adding two of them on here. We're just showing you that either one of those is fine. Okay, that was a lot to wrap our heads around because we're still learning how to use these charts. I think that's enough. We're up to almost 31 minutes. So we're going to stop there. We'll catch up to you next time.